Wye-Wye transformer connections have been used for decades with generally satisfactory performance. However, there are some potential field performance and safety issues that should be considered. Firstly, harmonic resonance. Wye-Wye connections can create a closed path for harmonic currents, potentially leading to harmonic resonance. Harmonics can cause transformer overheating, increased losses, and premature failure. Secondly, ground faults. With both neutrals bonded and grounded, a ground fault on a high voltage side can result in high fault currents. The fault current can damage the transformer, cables, and switchgear. Thirdly, ferroresonance. This is a rare but potentially catastrophic phenomenon that can occur when the system is lightly loaded and capacitor switching occurs. Ferroresonance can cause overvoltages, arcing, and transformer damage. Now let us discuss mitigation measures. Firstly, minimizing harmonics. Use harmonic filters or other mitigation devices to reduce harmonic currents. Secondly, limiting ground fault currents. Install current limiting fuses or ground relays to limit fault currents. Thirdly, preventing ferroresonance. Avoid capacitor switching when the system is lightly loaded. Use special capacitor designs or install surge arresters. Some additional considerations should be taken into account. Firstly, local codes and practices. Wye-Wye connections may not be permitted in certain areas or by local utility companies. Secondly, reliability. Delta-wye connections are generally considered to be more reliable than Wye-Wye connections, especially in demanding applications with frequent ground faults. Thirdly, cost. Wye-Wye transformers are typically less expensive than delta-wye transformers. In conclusion, while Wye-Wye transformer connections have been used successfully in many applications, it is important to be aware of the potential field performance and safety issues. By taking appropriate mitigation measures and considering the specific requirements of your application, you can minimize the risks and ensure a safe and reliable electrical system. A 75 kVA 25,000/14,000 volts to 120/208 volts transformer is being planned with both neutrals bonded and grounded to a ground ring around the slab. Here is some more technical background. Harmonic resonance in Wye-Wye transformers primarily arises due to the zero-sequence harmonic currents. These currents, which are multiples of the third harmonic third, 9th, 15th, etc., circulate within the closed delta formed by the transformer windings and the grounded neutral. The impedance of the transformer windings and the system impedance at these harmonic frequencies can create a resonance circuit, leading to amplified harmonic currents and voltages. This resonance can cause several problems. Firstly, transformer overheating due to increased core and winding losses caused by the elevated harmonic currents. Secondly, voltage distortion, which can affect the performance of sensitive electronic equipment connected to the system. Thirdly, increased neutral currents, potentially overloading the neutral conductor and causing nuisance tripping of protective devices. Fourthly, premature aging of transformer insulation due to the combined thermal and dielectric stress from the harmonic voltages and currents. To mitigate harmonic resonance, several strategies can be employed. Firstly, harmonic filters. These are tuned to specific harmonic frequencies to provide a low impedance path for the harmonic currents, thereby preventing them from circulating within the transformer windings. Secondly, K-rated transformers. These are specifically designed to withstand the heating effects of harmonic currents and are often used in applications with significant nonlinear loads. Thirdly, phase-shifting transformers. Using a delta-wye transformer connection can block the flow of zero-sequence harmonic currents, preventing them from entering the system. Fourthly, reactor impedance. Adding impedance in a neutral path can help to detune the resonance circuit and reduce the amplitude of harmonic currents. Ground faults in Wye-Wye transformers with both neutrals bonded and grounded can result in high fault currents for several reasons. Firstly, low impedance path. The grounded neutral provides a low impedance path for fault currents to flow back to the source. Secondly, high fault current magnitude. The magnitude of the fault current is determined by the system voltage and the impedance of the fault path, which is typically low in a grounded system. Thirdly, rapid fault current rise. The fault current can rise very rapidly, potentially exceeding the interrupting capacity of protective devices. Fourthly, equipment damage. High fault currents can cause significant damage to the transformer, cables, switchgear, and other electrical equipment in the fault path. To limit ground fault currents, the following measures can be taken. Firstly, current limiting fuses. These are designed to quickly interrupt the fault current, limiting the amount of energy that is dissipated in the fault. Secondly, ground fault relays. These detect the presence of a ground fault and trip the appropriate protective devices to isolate the fault. Thirdly, impedance grounding. Adding impedance in the neutral path can help to reduce the magnitude of the fault current. Fourthly, high resistance grounding. This limits the fault current to a low level, reducing the risk of damage to equipment. Ferroresonance is a nonlinear resonance phenomenon that can occur in lightly loaded power systems with inductive and capacitive elements. In Wye-Wye transformers, ferroresonance can be triggered by capacitor switching or other disturbances that introduce a sudden change in voltage or current. This can lead to overvoltages, arcing, and transformer damage. The following factors contribute to ferroresonance. Firstly, nonlinear magnetizing inductance. The magnetizing inductance of the transformer core is nonlinear, meaning that it changes with the applied voltage. Secondly, capacitance. Capacitance in the system, such as from cables, capacitors, or surge arresters, can interact with the nonlinear inductance to create a resonance circuit. Thirdly, light loading. When the system is lightly loaded, the damping effect of the load is reduced, making the system more susceptible to ferroresonance. To prevent ferroresonance, the following measures can be taken. Firstly, avoid capacitor switching during light load conditions. Capacitor switching can create a sudden change in voltage that can trigger ferroresonance. Secondly, use controlled switching devices. Controlled switching devices can minimize the transient voltages associated with capacitor switching. Thirdly, install surge arresters. Surge arresters can protect the transformer from overvoltages caused by ferroresonance. Fourthly, use special capacitor designs. Some capacitor designs incorporate damping resistors to reduce the risk of ferroresonance. Fifthly, ensure sufficient load. Maintaining a minimum load on the system can help to damp out oscillations and prevent ferroresonance. Local codes and practices may restrict the use of Wye-Wye transformer connections due to the potential for harmonic resonance and ground fault issues. Utility companies may also have specific requirements for transformer connections to ensure the safety and reliability of the power grid. It is important to consult with local authorities and utility companies to determine the acceptable transformer connection types for a particular application. Delta-wye connections are generally considered to be more reliable than Wye-Wye connections, especially in demanding applications with frequent ground faults. This is because delta-wye connections do not provide a path for zero-sequence harmonic currents and can limit the magnitude of ground fault currents. Delta-wye transformers are also less susceptible to ferroresonance. However, delta-wye transformers are typically more expensive than Wye-Wye transformers. The cost difference is due to the more complex winding configuration and the need for additional insulation to withstand the higher voltages. The choice between Wye-Wye and delta-wye transformers depends on the specific requirements of the application, including the load characteristics, the presence of harmonics, the grounding requirements, and the cost considerations. In general, delta-wye transformers are preferred for applications where reliability is critical and harmonic distortion is a concern. Wye-Wye transformers can be used in applications where cost is a primary consideration and the potential risks of harmonic resonance and ground faults can be mitigated through appropriate design and protective measures. The application of a 75 kVA 25,000/14,000 volts to 120/208 volts transformer with both neutrals bonded and grounded to a ground ring around the slab requires careful consideration of the system grounding. Grounding both neutrals creates a solidly grounded system on both the high voltage and low voltage sides of the transformer. This provides a low impedance path for fault currents, which can improve the speed of fault detection and clearing. However, it can also lead to higher fault currents and increased stress on equipment. The ground ring around the slab provides a low-impedance ground path for the entire system. This helps to equalize ground potential and reduce the risk of electric shock. The size and configuration of the ground ring should be designed to meet the requirements of applicable codes and standards. It is important to coordinate the grounding system with the protective devices to ensure that faults are cleared quickly and safely. The selection of protective devices, such as fuses and relays, should be based on the expected fault currents and the coordination requirements of the system. It is also important to consider the impact of harmonics on the performance of protective devices. Harmonic currents can cause protective devices to operate incorrectly, leading to nuisance tripping or failure to trip when a fault occurs.